admit it's been a bit of a rough day. So, this is gonna seem like a bit of an overreaction, but I don't think I did too hot on the quiz and discussion today, which was a little bit frustrating because I understand everything behind the concept. It was the decomposition of the acceleration vectors that we covered yesterday, except I didn't realize that if you just attempted to go through and take the hard derivatives, the derivatives get ridiculously complicated ridiculously quickly. So I ended up just sort of stopping in the middle, and I didn't know there was a strategy behind it that could actually make the problem doable. So, no new material, but that is something that I'm going to need to cover tonight, because midterm is on Friday, and I can almost guarantee that this is going to be on the midterm on Friday. So, I should do that tonight. Another thing that I learned today was that I need to get the homework done before the Tuesday quiz section. Even though it is due on Thursday, I cannot do well on the quiz unless I have done the homework and made sure that I understand the concepts. So I'm going to have to start making my own schedule, no longer dependent on due dates. Of course, we're still going to be doing the homework before the due date. That's pretty important. Another thing that I think I learned today is I need to find another activity besides being on my computer that is relaxing for me. I spent an obscene amount of time binging on my computer today, which is unacceptable and an unsustainable activity. So I think that I'm going to try replacing my computer with reading when I need to relax. So with that, let's actually cover this topic properly, shall we? So let's say that we're given the following position vector. And let's say we want to get it into its acceleration form of v prime times t, which is the tangent unit vector, plus kappa times v squared times n, which is the unit normal vector. We first take the derivative, which is equal to the velocity vector v. The speed v is going to be equal to the magnitude of the first derivative vector, which in this case is going to equal the square root of 1 plus 4 sine squared t plus cosine squared t. Okay, like, I just pulled a problem from the textbook, and I was trying to do it by myself and then check in the textbook to see if I was doing it right, but I couldn't find anything in the textbook, so I checked on Slater, and apparently in this chapter they don't tell you how to decompose these complex vectors, because just take a look. If we tried to take the derivative of the speed equation v, this is what happens. This is just the derivative of the inside. We still need to do chain rule. So now we've multiplied by the derivative of the outside. So let's try simplifying this a little bit and seeing if anything comes of it. I mean, it looks less complicated. Oh, I forgot the dt. Never forget your dt, kids. I mean, it looks less complicated. Oh, for goodness sake. I mean, it looks less complicated, but it still doesn't look very fun to work with. And I think to compute, to plug all these things into the necessary equations for, the tangent unit vector and the normal unit vector would be a little bit ridiculous. Especially when we can just find the... Hold on a minute. So we know that the total acceleration vector is going to be given by r double prime. But what I'm thinking is there a way to decompose this thing into unit, normal, and tangent vectors using some of the things that I've used in my other classes? I don't think there is, but let me try. So this was a bit of wild goose chase because t and n are not the things that we're having trouble finding. The things that we're having trouble finding are things like v prime and kappa and v squared, because they just get so complicated so quickly. I think that it might help to find n a little bit if you were to take the... this is going to be complicated. If you were to, say, take r double prime of t and find the angle between, let's see, how would you do that? You would need to find the angle between it and the horizontal, and then from that you could use dot products to find the angle between the normal vector and r double prime. But no, you don't know the magnitude of the normal vector. Oh dear. I'm really frustrated about this too, because I totally understand that you can split up acceleration into acceleration in a tangent direction and acceleration to a normal direction. You can define a curve by doing that. I totally understand that. I understand that velocity is given by the first derivative. I understand that acceleration is given by the second derivative. I understand all of that. It's just, it's a technical problem. But I have faith that I can get this. So, the good news is there is calculus lecture tomorrow, and of course our professor is going to be there. Now, there are a couple possibilities. A, he goes over this in class, which would be kind of shocking considering that this was on the quiz. Or B, he doesn't go over it in class and I can just ask him afterwards. Worst case scenario is I can go into either TA office hours or his own office hours to ask him about this. Because this is the Goliath to my David. I am Sherlock, this thing is Moriarty. But let me tell you, good always triumphs over evil. And this thing's been pretty useful to a lot of people. Me, not so much. There's plenty of time for me to get this, I just need to be proactive about it. It'll all start in calc lecture tomorrow. But that's not all I have to cover for tonight, because we have a statics quiz tomorrow. I just realized how far behind I actually am. Now, I'm being a little melodramatic because I'm not behind in the things I understand, rather the things that I've covered in these videos. But this little catch-up tonight will serve as good reminders for me for the quiz tomorrow. So let's get started. Oh my lord, it has been a while since I've studied statics on my own time. Because last time we were introduced to the principle of transmissibility, which basically states that you can move a force anywhere along a line on a rigid body that points in the same direction as the force is acting, and it will still have the same effect on that rigid body. But let us for a moment table the principle of transmissibility and instead begin to look at moments of force. The basic idea behind a moment of force is that a body can influence a point from far away. And depending on the distance that that body is from that certain point, the effect can be greatly exacerbated. For example, both of these boxes are exerting a moment of force about the point in the middle of the seesaw. Getting into defining moments with a little bit more mathematical rigorosity, that isn't a word. Getting into defining moments of force mathematically, we see that if a force is applied perpendicular to a line that is drawn from its tip to the origin, and it is perpendicular to that line. Did I already say that? I think I did. If a force is acting perpendicular to a line drawn from it to the origin, then the moment of force is equal to the magnitude of the force vector times the distance. Now we notice that depending on which way this thing is rotating, it's either going to be positive or negative. It doesn't matter which direction is positive or negative, we just need to be consistent. Or if we are told which direction is positive and which is negative, then I guess we need to be even more consistent, right? But this is only the simplest case, because things only get trickier from here. Because any generic moment of force is going to be defined by the cross product of R and F. Now we notice that F's line of action does make a perpendicular with D. But D isn't the thing we're worried about. We're worried about R. And R is the position vector that runs directly from O to the point where F is applied. And then theta is the angle between the line of action and R. I lied, theta is the angle between the force vector and R directly. Now it always, always, always needs to be R cross F. It can never be F cross R. Always R cross F. But before we continue, let's quickly touch on Variginon's theorem. It basically states that the moment of force generated by a bunch of forces acting on the same point will be equal to R cross the sum of all of those forces. But the forces need to be acting at the same point in order for this theorem to apply. So we can use Variginon's theorem to find a moment of force by decomposing a force vector into its component parts, and also decomposing a position vector into its component parts. Which means that the moment of force is going to be equal to the determinant of R cross F. But there's a little bit of an easier way to do this. At least there is a way to do this if you're not given coordinates. One where you don't actually need to decompose anything. Because the magnitude of the moment of force is going to be equal to the magnitude of R times the magnitude of F times the sine of the angle between R and F. So, let's imagine that we have a lever that is 24 inches long, and we have a force being applied at the end of that lever at a certain ungiven angle. The lever is right now 60 degrees above the horizontal, and the force is perpendicular to the horizontal. So, what is the moment of force about O? Using everything we've learned, we can find out easily. First of all, we know that the angle in between R and F is going to be 30 because all the angles in a triangle add up to 180 degrees. We already have two angles, 60 and 90, 60 and plus 90, 180. I've forgotten how to add. 180 minus 60 plus 90 is going to be 30. I forgot to put that the force's magnitude is 100 pounds. So we know that the magnitude of the force is 100 pounds, and we know that the magnitude of the vector R is going to be 24 inches, which is just the distance from the point O to the point of application. We'll call it A. So from our new equations, we get that the magnitude of the moment of force is going to be equal to 1,200 pounds inches. Now, in order to determine directionality, we use the right-hand rule. So we put our arm along R and curl our fingers towards F, and we notice that the thumb points into the board, therefore, M0 is going to be equal to negative 1,200 pound inches. Ta-da! But things get even more complicated from here, because we're not always going to be taking moments of force around points. What if instead we wanted to take a moment of force about an axis? For the sake of simplicity, I am already decomposing this force vector. I'm also giving myself some dimensions for this axis. Keep in mind, none of this is to scale. So first we need to define R, the position vector from one of the points on this axis to our force vector. Let's say that it is from A to the point of application B. Okay, I'm missing things because I'm getting tired, but I'm going to go over the gist of it. Here's the gist. R is going to be some position vector from some point on the axes to the point of application. F is going to be made up of the components x, y, and z of the force vector F. Lambda is going to be a unit vector in the direction of the axes. And since I am pretty confident on how to find unit vectors, I think I am just going to leave these as variables for the night. The moment of force about the axis OA is going to be the triple product, lambda dot the quantity of cross product R cross X. And the triple product is going to be given by the determinant of this matrix. So we remember that when we were finding the cross product, that this top row was filled by I, J, and K. That's not the case anymore. But we still do the plus minus plus thing that we were doing with the regular cross product. And I'm caught up. That was pretty good. I feel good about these topics. I guess we're just gonna have to wait and see. I am naively optimistic, so I'm gonna take that quiz and I'll report back tomorrow, but until then, thank you all for watching. See y'all tomorrow.